Okay, so now officially, hello everyone. Welcome to episode 17 of Warsaw.ai meetup. Today, we have pleasure to host three great speakers. So first, Łukasz Kuciński from Polish Academy of Sciences will give a talk, Be Like Water, Adaptive Subgoal Search. Then Maciej Wołczyk, Jagiellonian University from Krakow, will give a talk, Greedy Robots in a Changing World, Forgetting and Transfer in Continual Reinforcement Learning. And finally, Krzysztof from Poznań University of Technology, Learning Terrain Representation for Legged Robot Localization. Finally, there will be after party with networking, so we hope that you will stay with us until the end. All right, I think we can start. So, Łukasz, if you are ready, the floor is yours. So thank you, first of all, for accepting our invitation, and we can start.
Thank you very much for a kind introduction. So it's great to be here. Big thank you to the organizers for inviting me, and thanks to the sponsors for making this event possible. My name is Łukasz Kuciński, and I will be talking about adaptive subgoal search. And I will talk about it from perspective of adaptivity, hence the reference to the famous quote of Bruce Lee about be water, as water being the embodiment of this perfect adaptive entity. All right, so adaptivity is ubiquitous. It's in biological systems, in our daily lives, the way how our brain works, how it switches from system 1 to system 2. But I will talk more about computational side of adaptivity, in particular in the context of reinforcement learning. So why reinforcement learning? So partly because I'm involved in the field, but mostly because this is such a convenient stage to talk about adaptivity. Okay, so what is reinforcement learning, or what does it do? So reinforcement learning is related to interacting with the world, making a sequence of decisions and maximizing rewards. So if you are not familiar with RL, you can think about it as playing a video game where the world is the game and you act in the game and you get scores and you want to maximize your score. And in this research that I will be talking about, we considered two games and one kind of inequality proving environment. So the first game is a Sokoban, so some of you may know it. It's a logical puzzle when you control this agent Kenny, and Kenny can push objects, the boxes, and to solve the board, he has to push all the boxes into the designed cells, here shown by this diamond. Okay, so Rubik's Cube is kind of known to pretty much everyone. And the last one is int. And so this is kind of pictorially showing how you can see state and action in this environment. So these are games, but they are hard combinatorial problems. In particular, Sokoban is NP-hard. And these are convenient test beds for testing our algorithms. And the hope is that one day we'll be able to fully solve high impact problems, such as automated theorem proving, algorithm design, program synthesis, retrosynthesis, robotics. And there are quite a lot of progress and successes in the field. So this is not an unfounded hope. Okay, so let's see how reinforcement learning kind of behaves. What is the trajectory in reinforcement learning? How can you act, and how do the data look like? Okay, so this is a trajectory. You can see that you start in the upper left corner, and Kenny has to put those two boxes into the place. And if you look at the lower right corner, he succeeded. So these are the consecutive steps that Kenny took. All right, and so the board is a state. And then action is represented by this cross here. So in this state, Kenny will take action right. And as you expect, he will move right. Well, and for each action, the game or environment will return rewards. Here, for going right, we receive nothing. But as you can see, Kenny moved here, and then he will go upwards, which will result in placing the box on one of the designed places, and he's rewarded with this small coin and so on. So this all continues like that, and this is how a typical kind of enrolling of an RL strategy will look like. This is the data that you will collect, and this is pretty much how RL looks in practice. Okay, so I will try to convince you that a lot of things in RL are related to adaptivity. So first of all, you may say that the very problem is adaptive because you want to find a strategy that, depending on the state that you are in, will result in actions. So this is commonly known as policy. Here, Kenny sees a state, thinks about it, what to do, and comes up with an action. So you adapt to the state. Another thing, you can consider a environment like this. There is a corridor, and there is a mushroom which gives you a small reward, and a diamond that gives you a lot of reward, a high reward. So we know this, but assume for a moment that there is a fog in this corridor, and Kenny doesn't know it. So chances are that he will arrive to the mushroom first, and then if he will not adapt to what he doesn't know about the environment, he might tend to go to the mushroom all the time, not discovering that there is a bigger prize there. So you have to adapt to what you don't know. Okay, during the execution of the game, you collect data, and you have to, so the data is your experience, and you have to adapt to experience. And so pretty much learning is adapting to experience. But also you may try to rehearse or replay the things that you've done wrong. So you made several mistakes, which are here denoted by X's. And you might try to rehearse or replay those experiences more often to not make mistakes the next time. Okay, another part of adaptivity is adapting to the problem complexity. Maybe the problem that you want to solve is hard, and maybe you want to break it down into smaller sub-problems. And you start with learning something simple, like on the left, and then if you master that, you learn something more difficult and more difficult. This is kind of similar to how we learn things. And there are a lot of approaches and ways to do it. So you don't have to construct like this explicit curriculum. You can rewrite history, or you can create some kind of self-play. All right, so you can also adapt to state complexity. So we arrived at adaptive subgoal search. These wonderful gentlemen are my collaborators. So this is a joint work with Michał Zawalski, Michał Tyrolski, Konrad Czechowski, Damian Stachura, Piotr Piękosz, Tomasz Odrzyguść, Tony Wu i Piotr Miłoś. So we talked a little bit about adaptivity. So let's talk a little bit about subgoal search. Okay, so here we've got a Kenny in some state, and there is a prize on the right. And here is a graph showing you the graph of the game. So for instance, you can consider a game of Sokoban, then you can expand the whole graph of the game and apply some kind of a graph search algorithm. So if we apply BFS, for instance, it will try to visit all the nodes and all the edges, and finally it will find the solution. So the problem with this approach is that it doesn't scale very well with branching factor and number of nodes. So, well, it is obviously known, and there are a lot of ways of improving this situation. So people have been trying to marry these kind of algorithms with learning. And one of the approaches is subgoal search. Okay, so this is subgoal search. And the idea is not to transition by atomic actions, but operate on a higher level of abstraction. So here, this higher level of abstraction are nodes that are distant by several steps. So in here, this distance is 2, and we will perform our search on this subgraph of subgoals. Okay, so in order to make it work, you have to introduce several components, which I will define when we'll talk about adaptive subgoal search. Okay, so adaptive subgoal search is a similar concept, although now we don't really force the subgoals to be equidistant between one another. Maybe we can just adapt to complexity of the state. So if a state is easy, maybe we can make larger moves. We can reach further subgoals from easy state. And if a state is hard, maybe we need to do this exhaustive search. So here you can see there are jumps by 3 actions, by 2, and by 1. Okay, so in order to pull this through, what are the key components? Right, so we have to have a way to generate subgoals, okay? So this would be subgoal generator or subgoal generators. We also want to somehow score subgoals, giving them value. And then, even if we solve this subgraph of subgoals, we still at the end have to connect the dots, connect the subgoals using atomic actions. So we have to have some kind of low-level policy or controller that can achieve that. Okay, on top of that, we obviously have to have a planner to even reason about planning. So up to this point, this is almost subgoal search with the difference that distances between subgoals can be different, can be non-constant. So this very thing that we can adapt the length, the distance between subgoals is adaptivity here. And I will, so this got cluttered very fast and it was kind of on purpose, but I will try to unpack it a little bit now. So key components, right? Value or value function is a basic concept in RL, and it assigns a value to a state. Here, this value would be a distance to a goal, and since we usually want high values to be good, we give a negative distance. There is also a low-level policy which tells you, okay, I'm starting from a state, I want to arrive to a subgoal, and which action should I take? So these kind of answers are given by the policy. Subgoal generator generates subgoals from a given state. And then the planner here in this work is best first search. And the adaptivity mechanism here, which is the main driving force of the results that I will be talking in a minute, kind of relies on the rule of optimism and also on a kind of cautious optimism, so to speak. So value, low-level policy, and generators are neural networks, and you can think about them as transformers. And subgoals could look like this. So we start from the board in the lower left corner, and then each subgoals relies to putting one of the boxes on the designed places, and each subgoal is a 3 subgoal. And in this example, we could have 2 subgoals, meaning distance by 2, 5 subgoals, 1 subgoal, and so on, and 10 subgoal. Right. So how does adaptivity work here? So the adaptivity relies on optimism, which means that if you're in a state, go as far as you can. So pick a subgoal which is the farthest away from your state and the one that you can reach. And if there are many, break ties using value. Okay, so this looks kind of easy to write, but hard to pinpoint. For instance, you would think that you would always want to go as far as possible. But the problem with that is that it's hard to generate faraway subgoals, and it's hard to validate that we can reach them. And what's cool about this approach is that you can really implement it as a, it boils down to defining appropriate priority queue, where the priority is just a pair of distance and value. And obviously, since you use models, learned models, you can have errors. And you will not pull this through if you do not have a way of saying, okay, can we validate that this subgoal is valid? And there are 3 ways of doing it. So first, you can train a neural network that classifies that your subgoal is correct. Then you can use your low-level policy to ask, can I reach this subgoal? And finally, if you have your path to the solution, you can check if all the subgoals are correct. All right, so something about results. So what you can see here is these are not learning curves. These are curves that show you the dependence. Okay, how well do we do, measured by success rate, given a computational budget? So computational budget is on an x-axis and success rate is on y-axis. And what you should look at is kind of the left-hand side of the plot and the right-hand side of the plot. So the left-hand side shows you how well do we perform in low budget regime. And on the right, how well do we perform in high budget regime. And it turns out that in both cases, ADA sub S works the best. And maybe the most striking result is here for inequality proving environment, where, for instance, for graph budget of 50 nodes, all baselines struggle, but ADA sub S already has like 60% solved rate. And if you look on the right-hand side for high budgets, you see that they are somewhat close if you look at the objective values, but being close to 100% solved rates, well, in this regime, you deal with hard problems, right? So small differences can in fact translate to big difference in algorithms. And what really helps here is to, instead looking on solved rates, compare failure rates. And for instance, you would deduce that for int, for example, ADA has twice lower failure rate than K sub S. Okay, so the last slide about results is looking at the out of distribution performance. So what we did here is we trained ADA on inequality proving environment for tasks with proofs of size 15, right? And we ask ourselves, okay, so we have this problem, this algorithm, and how does it perform for longer proofs? So on x-axis, you see proof length. So for instance, here we see that ADA sub S trained on proofs of length 15 perform, like have 93% solved rate for proofs of length 17. So there are 2 things that you can see here. First is that the decay rate is much slower for ADA than K sub, meaning Subgoal Search. And second of all, you see that the difference is the biggest for the harder cases, the most out of distribution cases. And it turns out that majority of the kind of, you can ask, okay, what is the reason for this improvements of performance? And the answer is that majority of that comes from this adaptivity improvement. Okay, so to wrap this up, what are the key takeaways? So one is search using subgoals, not atomic actions. Another one is adapt to state complexity. And third is that ADA sub S is good at solving hard combinatorial problems. So what's next? And there are two lines of research coming from it. So first is how can we improve already existing components in ADA sub S? So maybe we can improve learning protocol or plan in latent space, or maybe somehow learn to generate goals in an automated manner, or maybe use it for multi-agent setup, and so on and so forth. And what would be the applications? Okay, so it seems that ADA sub S is good at solving hard combinatorial problems, so why not apply it to automated theorem proving, program synthesis, algorithm design, or robotics. And a lot of the things that I mentioned are in some way of shape or form projects that are ongoing or on the list to be done. All right, so thank you for your attention. You can see the links to the papers here. And if you have any questions now, please do ask. But if you have any questions later, also you can send me an email or chat with me afterwards. Thank you very much.
Thank you, Łukasz. Thanks very much. Very interesting presentation. Do we have any questions to Łukasz? Maybe I can start. Can you maybe tell a bit more about the architectures that you use for training and the process of training? So, for example, the computational power that was required and time of training.
Right. So we use transformers mostly, and the reason is that this is a general purpose kind of good architecture. Like it is not necessary for these problems. They are just good models for many modalities, right? And as to learning, they were trained in this project on offline data. So they were trained in a supervised manner. And one of the follow-up research projects is to make a self-improvement loop. So train them in classical RL setup. And as to the data, so they were gathered differently for different environments. So for instance, for Rubik's Cube, we scrambled solved cube like 20 times randomly and then reversed the process. So this was the data, easy. Similarly for int, we generated, so the environment allows you to generate inequalities procedurally. And for Sokoban, we used one of our previous works to use a strong MCTS agent to solve it and generate data. Right. So there are more details when it comes to this. And if you're interested, you can look in the paper because this is a good question and quite a lot of effort was put into answering these kind of problems.
Great. Thank you. Thanks for the answer. Oh, we have one more question.
Hi, thank you for the talk. Do you have any plans to work on the continuous domain?
Okay, thanks. Yeah, that's a great question. And in fact, we do. So that's why there is a robotics there. So it turns out that there is quite a lot of work done in terms of offline RL or in general, training offline and deploying online on robots and fine-tuning, kind of. And a lot of those approaches, they try to utilize conditional policies. So if you train conditional policy offline, then online the question is, can such a policy solve the out-of-distribution problem? So then the answer is yes or no. Yes, if the answer is yes, then great. If not, then you've got problems of fine-tuning it because you would have to feed it the sub-goals because this is a conditional policy, right? And then you can use these kind of techniques to creating a curriculum of sub-goals for such a policy, for instance. So there are a lot of approaches to do it. Currently, nobody uses this kind of stuff, but this is on our radar, and I think that it can be promising.
All right, great. Thanks for the answer. Thanks for the question. Do you have more questions to Łukasz? If not, then I think we can thank once again Łukasz for a great presentation. Thank you. And we can invite our second speaker, Maciej.
Thank you. All right, so my name is Maciej Wołczyk. I'm a fourth-year PhD student at the Jagiellonian University. Thank you for your invitation. It's very nice to be here. Today I will talk about greedy robots in a changing world. So my talk will also concern adaptivity in some sense, but I will focus more about adapting to changes in the environment, rather the kind of adaptivity that Łukasz was talking about. The talk is based on two papers, one which was published at NeurIPS 2021, and another which was published at NeurIPS 2022. Both of these works have the same set of amazing co-authors from the Jagiellonian University, Polish Academy of Sciences and DeepMind. So yeah, I thank them for their cooperation on those works. And yeah, let's get going. All right, so the world is constantly changing, and it is changing in pretty big ways. So in particular, all of our lives were impacted quite a bit by COVID, and they might also be impacted by drastic changes in terms of the economy. But there are also many more mundane ways of how the world around us is changing. So for example, if you go to a completely new place that you haven't been to before, you might have to learn local customs and local laws. The world has also changed for me today, because this is the first time I'm here in this building giving a talk. So this is, you know, another kind of change in the world. And we as humans, we do not really notice all of these small changes, because we are naturally very good at adapting to all kinds of changes. All right, but this is not true for deep learning models. For deep learning models, the world is usually completely stationary. And what I mean by that is that we usually train them just once on a perfectly static data set that does not change at all during the training. And if we encounter any new data, we just pre-trained on the data set from scratch, starting from the beginning. And obviously, if we assume that the world really is constantly changing and we want to deal with that, this is not a very good strategy. A better strategy, which emerged recently, is to divide the life of a deep learning model into pre-training and fine-tuning. So big foundation models, such as BERT or GPT-3, they first pre-trained on some kind of big data set, which contains many different types of data. And then they fine-tune on a downstream task that we actually want to solve. So we are able, in some sense, to adapt to this particular task that we want to solve. But I would argue this is still not flexible enough, because sometimes we would also like to fine-tune our pre-trained model. We would like to update it. So for example, we would like to tell GPT-3 about what the world looks like in 2023. And the easiest way to do it is probably just retraining it from scratch. So again, this is not very efficient if we really want to deal with this, with all kinds of changes in the world. All right, so the ideal model for a world that is constantly changing is to continually learn. So basically, learn and adapt to the data as we go, constantly fine-tune on the new data, and deal with the data shift that occurs. This sounds great. So you might ask why we are not using it, why we are still using this kind of more static approach to learning. Well, the answer is pretty simple. Continual learning is hard. It is really difficult. And it is difficult because deep learning models are inherently greedy, by which I mean that they apply all of the available resources to the current task. And they kind of disregard all of the data that they saw previously. So just to give you a quick example of what I mean, imagine that we have a simple classification task where we want to classify whether there's a cat or a dog in the picture. And we train our neural network on this task, and it does pretty well. And then we take this pre-trained network and we train it on another task. This time we want to classify whether there's a bird or an airplane in the picture. And again, it will learn this task pretty well, but something else will happen. We will completely forget how to perform the first task. So the network being greedy and putting all of the computational resources towards the second task will forget how to solve the first task. So when it sees a picture of a cat or a dog, it will be very confused. And we call this kind of phenomenon catastrophic forgetting, and it appears everywhere. It is kind of independent of the setting, independent of the network architecture, and also the particular type of data shift. Here we totally change the task, but even if the type of the data shift is more subtle, we will still observe this. We will still observe this phenomenon. And I would argue that this type of problem is especially pressing for reinforcement learning for robotics, because robots have to act in the real world, and as I'm constantly saying, the real world is constantly changing. There are many different types of data shift that might happen. So you might have different objectives, you might have different environments, there might be changes in terms of the weather, there might be wear and tear of the hardware, lots and lots of stuff might change. And another reason why I think reinforcement learning for robotics is an interesting goal for continual learning is that it might be dangerous to gather data with untrained models, right? You don't really want to use a model that is completely random to act in the real world, as it might cause some harm. Well, the bad news is that there is relatively little work in continual reinforcement learning. Most of the work in continual learning is done for supervised learning for problems such as classification or regression or semantic segmentation. And although this, having this rich literature on those topics is very nice, there are some problems in continual reinforcement learning that are not present in supervised continual learning. So we cannot really, solve them with supervised continual learning methods. And for example, there are questions like how to explore. So how to gather data in continual reinforcement learning. We do not have this problem in tasks such as classification. We have to deal with complex RL objectives, which are sometimes more complicated than empirical risk minimization that we have in supervised learning. And we also have to work with non-monolithic architectures, such as ones that are present in actor-critic algorithms. So given those challenges, we set ourselves a goal. We wanted to create a continual reinforcement learning benchmark, identify major problems in the setting, and start fixing them. Okay, but before we go to that, let me give you a quick glimpse of how continual learning methods usually perform. How do they make deep learning models less greedy? Well, they usually are classified in three different families. First of all, replay-based methods, which keep some kind of buffer of past data and then rehearse on this buffer to kind of try to remember what has happened before. There are modularity-based methods, which keep separate parts of the network for different tasks. And this way, they avoid the network being too greedy, as it has, a separate part for this one particular task. And there are methods based on regularization, which limit the changes in the network, especially for the parameters that are crucial for the previously encountered tasks. Okay, and those methods are pretty well tested in supervised learning, but not as much in reinforcement learning. So in order to fix that, we introduced Continual Word. So we defined a bunch of robotic tasks, which are similar in terms of the semantics. So for each task, we have this robotic hand, which is supposed to achieve some kind of objective. For example, in one of the tasks, it's supposed to pick up a hammer and hammer in a nail. In another, it is supposed to close a window. So although we have very similar semantics, there are different dynamics and different objectives between the tasks. So we have those tasks, and we using them, we create a sequence of tasks. And we test continual learning methods by training them on the sequence. So first we start with the hammer task. We train for 1 million steps on this task. Then we go to push wall. We train for 1 million steps and so on and so on. And the changes in the task represent some data shifts that happen. Okay, and when we test on this sequence, we compare the different continual learning approaches in terms of 3 major metrics. So the average success rate, so how many tasks we can actually solve at the end of the training. Forgetting, so how much performance on previous tasks dropped since we last visited them. And forward transfer, so how much can we gain from previous task? Can we use the knowledge obtained from the previous task to learn more efficiently on the current task? All right, and just to give you a quick overview of the technical details of our benchmark, we use the soft acrocritic algorithm as a base RL algorithm. It is very often used for robotic tasks. We implement several methods which cover all of the families which I described previously. We run over 50,000 experiments where we do a careful sweep of hyperparameters for each method, and we make sure that our conclusions are statistically significant. So we use a lot of seeds. We look at sequences of different lengths and orderings and many other ablations. We shared the code, so the code is publicly available, and thanks to that, several publications already used our benchmark for experimental analysis, which I think is extremely cool. Yeah, and I'm very proud of that. And yeah, in terms of the technical details, please, if you are interested, find more in the paper. Here, I will just focus on the conclusions and the observations that we made. All right, so let's get to the results. First of all, we made a lot of interesting observations from the perspective of continual learning. Standard methods which work very well in supervised continual learning require a lot of tinkering to make them work in reinforcement learning. Many continual learning methods behaved quite unexpectedly. So some of them behaved better than we expected, some of them behaved worse. This was all quite surprising. But there is, and the exploration policy is quite crucial. But there is one particular point that I would like to focus on, since it's very important. It is the trade-off between forward transfer and forgetting. So we found out that our methods do not forget. So in this particular setting, we can say that the problem of catastrophic forgetting is fixed, but they also do not transfer. So in particular, just to give you, just to remind you, when I say transfer, I mean how well we can reuse the past data, the past knowledge, past experiences to learn more efficiently on the current task. And if we only look at the transfer, it appears that simple fine-tuning, which does not use any kind of smart continual learning method, it performs best in terms of forward transfer. And this means that for this particular case, retaining the knowledge, as the continual learning methods do, doesn't help us to learn the new tasks, which is pretty worrying. We would like to remember the past and also be able to use it. And in particular, there is one setting where this result is particularly worrying, and maybe I will just kind of describe it very briefly for the sake of brevity. But it appears that when we revisit a particular task, so when we start training on a particular task once again after visiting some tasks in between, the performance on this task is worse than when we first encountered it. So even though we already solved this task and we are supposed to kind of keep this knowledge, when we encounter it again, we cannot really solve it faster or more efficiently. So this leads us to a conclusion that continual learning methods can remember the past, but they cannot really reuse it. Okay, so that led us to ask the important question: what is going on with transfer? Why is it, why do we see things like that? Obviously, solving catastrophic forgetting is not enough, because like we would really like to see some transfer in this setting, and in order to understand this phenomenon a little bit better, we take the soft actor critic apart to understand the building blocks of transfer. And yeah, just to give you a quick overview of the soft actor critic algorithm and how we kind of took it apart, we divided it into the actor, which acts in the environment and is actually used for deployment, the critic, who evaluates the actions of the actor and is crucial for training, but it's not actually used after deployment. We only use the actor then. The exploration policy, which gathers initial data for each task before the actor learns anything useful, and also the replay buffer, so which stores the data for more efficient learning. So the actor and the critic do not use the data directly from the environment for training, but rather they use the data from the replay buffer to make the learning more efficient. And given those different components, we ask how important these are for transfer. And again, we ran a lot of experiments. We checked how transfer looks like for each of those components separately, on sequences of 2 tasks, on 10 tasks, and many different settings. And for the sake of brevity, I won't get into the details, and I will only share the main conclusions now. But please do take a look at our paper if you're interested. And yeah, so we found out that critic is crucial for transfer, but it is also very fragile from the perspective of optimization. So you cannot really apply any kind of regularization without it breaking, and regularization is really important for continual learning. So you really have to, the first lesson is to really apply regularization on the critic really carefully, and sometimes it is better not to apply any kind of regularization, which is kind of counterintuitive because we want to minimize forgetting in general. The next observation is that bad initial data in the buffer hurts a lot. So even if we have parameters of the actor and parameters of the critic, which are good for a particular task, if we populate the buffer with data that is random, that is not useful enough, we will see that the performance will not be very good, that the training will be quite slow. So the lesson here is to reuse previous policies for exploration, especially for the case where we have very long sequences and we have a lot of past policies to reuse. And finally, we found out that transferring the data is very important. So reusing the data from previous tasks would be very cool. But unfortunately, reinforcement learning objectives cannot really handle the interference. So if you just put all of the data that you have already seen in the buffer and try to train on that, it will completely collapse. It will be pretty bad. So in order to reuse this previous data, but at the same time, keep the learning going, we reuse the previous data through distillation using a supervised objective. So we perform a kind of behavioral cloning rather than resorting to reinforcement learning objectives, and this works quite well. And yeah, when we combine those lessons, we proposed a new method, which we call CloneXSAC. And the nice thing is that even though it is conceptually very simple, it consists of very straightforward tricks. It is able to outperform the other methods, especially in terms of forward transfer, which we really care about in this setting. And the nice lesson here is that being careful about the properties of your setting, in particular in this situation, it is reinforcement learning. So dealing with the setting very carefully, using right hyperparameters is often much better than using out-of-the-box solutions which work well in different scenarios. And yeah, even though this result is pretty cool, there are many secrets of transfer which we yet have to discover. So for example, one of the questions that bothers me is what is really being transferred? Is it something in terms of representation learning? Is it something about the training dynamics? Do we learn some kind of skills that we are able to use? Well, this is something that I hope to discover in the future. And yeah, that's all from me. Here are the links to the papers that I described. Here are the amazing co-authors of those papers. And the last thing is that I'm on the job market. So if you like this presentation and you would like to work with me, please reach out. And yeah, that's all. Thank you.
Okay, thank you, Maciej. Thanks for a very interesting presentation. We have our first question.
Thank you very much for the presentation and congratulations on the results. My question is about catastrophic forgetting and forward transfer.
Mm-hmm.
So you said that the methods you described basically solve catastrophic forgetting, but there are still problems with forward transfer.
Yes.
And you shown a plot. Okay, so I didn't really understand this, I guess. So my question is, if catastrophic forgetting is solved, but there are problems with forward transfer, and you are measuring this by retraining on a task that the algorithm was trained before,
Mm-hmm.
then so if we cannot learn to solve this task again to the same level, how is the catastrophic forgetting solved? I mean,
Okay, yeah, that's a very good question. There's one important detail that I kind of skipped here for the sake of brevity. But when we revisit those tasks, we basically use a different task ID. So the network doesn't really know that this is the same task that it has already solved. So we kind of say, okay, here is a new task and you have to solve it. But in reality, this task is exactly the same as one of the tasks we already solved. So yeah, this is a very good point. And yeah.
So like in your nomenclature, you would measure catastrophic forgetting if you would give the algorithm the same task ID again.
Yes, precisely. Yes.
Okay, thank you.
Yeah, thanks.
Thanks. Oh, one more question.
Hi, thank you for the talk. So the question is, did you have a chance or are planning to do this on the real robot? I mean, what is the reality gap? And then if you could just learn in simulation the task and then do the task which was not in the simulation stage.
Right. So yeah, this is also a very good question. We would really like to run some experiments on real robots, but I think we are not there yet, basically. So the nice thing about the simulation is that we can, run a lot of experiments. So those 50,000 experiments, those probably wouldn't be, viable in the real world. But yeah, I would really hope to, run some of these in the real world at some point. We don't have like plans for that in the near future, but in the far future, yeah, that would be great. Yeah, I'm not sure if I answered the second part of your questions. Could you repeat? Okay. Mm-hmm.
Okay, so last question.
Great, great talk, thanks. So regarding your comment that you need careful design for this solution to work, I'm wondering, did you test also how well that design then transfers to other tasks? I mean, slightly different benchmarks where you can, basically how much the hyperparameter tuning then is stable, or whether you have to start engineering again for the next task.
Yeah, that's a very good question. So in our work, we only use the continual word benchmark. We didn't really compare with other with other benchmarks. So this is definitely a limitation for our work. At the same time, we saw that within this benchmark, given different sequences, different orderings, and given many different ablation studies, our design choices kind of held up. So there wasn't that much noise in terms of the like hyperparameter selections. Hyperparameters that work well for one particular setting in our benchmark also worked pretty well for other settings. But yeah, I can't really say how would that hold up outside of the benchmark.
Okay, great. Thank you, Maciej. If there are more questions, Maciej will be later available during the after party. Thank you very much. Thanks once again.
Thanks.
Yeah, Krzysztof, it's your turn. You asked great questions, so now you can present your work.
Now it's my turn to get questions. Okay.
Yes.
My name is Krzysztof Walas. I'm from Poznań University of Technology. And at the beginning, I would say that I'm a little bit out of distribution. I come from robotics to AI. And I'm gonna have some real robots. This is why I was asking questions. So let me just briefly introduce myself. So I did my PhD at Poznań University of Technology, then the postdoc at the University of Birmingham. Then in my story, I got the LEADER project from National Center for Research and Development. Then I got Horizon projects, one on subterranean legged locomotion, which is part of the talk today. And also I'm leading now the deformable object manipulation project. I was lucky to work together with Marek and No Magic when they are starting the company. So I was helping them with robotics. I'm also a mentor of MAB Robotics, which is building legged robots here in Poland. And I'm organizing some Eurobotics Week or European Rover Challenge, and also some workshops at ECCV, ICCV, and ICRA. So my research is about perception for physical interaction. So I want the robots to interact with the physical world. And I'm quitting the assumption about object being solid. So most of the robotics is taking into account that everything is solid. So you have to avoid the objects, you have to avoid the collisions. And I think we should exploit the contacts and collisions, not to avoid them. And in my research, we have extensive use of haptic data and machine learning for signal processing. So I'm not pushing my research into computer vision because it's quite exploited, and the signal processing it's not. So I'm using some, in the work we are combining signal processing and computer vision, but we are mostly pushing in this direction of signal processing. What I want to have is to obtain the physical properties of the environment. So if I want to interact, I need to know the physics of the contact that I'm having with the world. And I'm applying this to legged locomotion and deformable object manipulation. So today's talk background is from 3 papers. 2 of the first papers is with the group from Oxford Robotics Institute. So this is collaboration from our joint project in Horizon 2020. So first one is on haptic Monte Carlo localization using geometric sensing and terrain classification. Then from terrain classification, we moved to unsupervised learning, and I will show the properties and what the switch gave us. And then just a sneak peek of the latest research that we did with the transformers on terrain representation. So as the motivational example, so I thought it might be good to have this link of the concept that I have in the presentation to some example that you might have in mind. So I would like you to imagine that you have a night mission to the kitchen. So you woke up in the middle of the night and you feel thirsty. So you need to get some water from kitchen, but you don't want to turn on the light because you don't want to wake people up in the flat. And you know the map of your flat because you are living there. And you are walking barefoot, so you cannot sense so you can sense the material on the floor. So you start in your bedroom and you start walking. You can start counting steps, and at some point you think you reach the doors, but you are not sure. It might be 20 centimeters away, 10 centimeters away. But when you feel this change, for example, from carpet to wood, so you have a wood in the corridor, you exactly know that you are at this point. And then you start counting steps. You are in the corridor, you have a couple of steps, and then you feel the difference between wood and ceramic tiles because now they are really cold. So you say, okay, I'm in the kitchen. So this is how we did with the robotics. So we were counting steps because our robot was blind, but we are using material properties for reducing the bias in this counting steps. So this is the problem statement. So we have a quadruped robot with 12 active degrees of freedom. And yes, it's hard to start RL from scratch on this robot because it costs 250,000 euros. So we didn't want to do that. So then we want to localize the robot against the prior map blindly. So the assumption is that the robot was used in the mines, for example, or so you can, for example, use your sensing system. So you have a prior map because you walked there, but then there was a collapse or something happened and you want to get back blindly, or there's a lot of dust, smoke, anything like that, and you cannot use your camera or laser scanner. So we are given the odometry and force torque sensing. So in the feet we have it's not showing up. So we are measuring force and torque. So we have a measurement of the interaction with the ground. And we assume accurate pose estimate availability to build the prior map. So we did it well. For example, having a good SLAM system. So in this supervised learning approach, this was the system that we had. So the heart of this is the sequential Monte Carlo particle estimator. So if you know the particle filtering, you should be familiar with that. What does it mean? But I will show in the next slide. We have the state estimator, so we more or less know where the robot is, so we can count steps. We have some feeling of the rotation of the robot from the inertial measurement unit. So this is what we have. And then we have our neural network, which is telling us about the terrain class. So this sequential Monte Carlo particle estimator is that we start without knowing where we are. So we put all the particles around the world that we are in. And then as gathering more data, the particles are converging to the place where we are. In this symmetrical world, we can have two clouds of particles, but at some point, we will find out where we are exactly. So in this case, we have some kind of laser scanner to gather information. In our case, we have feet of the robot to gather the information. And so we had a state-of-the-art network for classifying the ground. So it is our paper from 2019 and then 2020, together with our colleagues from ETH. So we did really good on the classification part. So we thought that we can join our forces with other teammates from the project from Oxford to put this classification together with the localization approach. And it turned out well. So just to briefly say what we had in the network. So we had those residual layers, which had the convolutional bits. We did this for signals, so it's 1D instead of 2D. And then from those convolutions, we have the proper representation to put it into the recursive part, which is on the right-hand side. Then we did some averaging, then fully connected layer, and then we had proper classes for the different terrains. And we also have those masks because we also, there's a problem for recursive neural network if you have a huge change of the length of the signal. So our signals were from 300 samples to 1,500 samples. So we solved this with this masking of the signal. And the results were, if you do, so the green one is the ground truth. This, let's say, violet one was the one when you are just counting steps. So as you can see, as you go, you are just diverging from the proper path because you don't have idea where to bias, what is your bias and how to reset it. And with our approach where we used geometric features plus terrain features, it is quite close to the ground truth. So the purple one, it's really close to the green one, with some exceptions. So there is part A and part B. So in the circles, the system is having some problems with the particles. So they are like diverging. But thanks to the approach that we have, at one hand side we have the geometry, so we can sense that there is, for example, change of the level, and then also in point B, the change in the type of the terrain, we are converging. So this is this converging part. But this was working pretty well, and also we discussed this today during Maciej's talk. If you are pushing the class, which is from human perspective, it is not totally related to the task. So for example, we have the, if we go back, we have the same type of terrain, for example, the carpet, the green one. At first it is on the flat ground, and on the other part it is on the inclination. And this gives you totally different sensing of force, but you are telling the system this is the same class. So this was like one of the problems that we had. And with unsupervised learning, so now our next approach is that we created the sparse latent map for this localization part. So instead of having classifiers on the classifier on the top part, we now have encoder, and in the encoder we have the latent vector. And this is the haptic autoencoder. It's quite classical autoencoder, but what we cared about is the latent vector in the middle, that we can represent the properties of the ground, let's say, in an unsupervised manner. So out of this, we get the map. So we were walking around to create this latent representation. So in the couple of runs, we had some kind of sparse map of the environment. And then using the some distance measure, when we are walking in the testing phase, we can say, okay, I'm close to this sparse points on the map, so I'm more or less in this terrain. But what is the difference here? If you do the classification, we had just the full homogeneous surfaces, and now we have those sparse samples. So we have more information in those latent vectors encoded. And for example, now we have the difference, which is shown in this picture now. There will be totally different latent vector for this carpet when it is on the inclined surface and when it is flat. So it will help us to find solve this ambiguity of the terrain, for example. And so the results are really good. And as you can see, when you are crossing the terrain now, we are no longer using geometry. It's just unsupervised learning and this sparse map. Whenever the system is diverging, when we cross the gap or we are at the same terrain, but having this slight changes in this unsupervised latent vectors, the system is converging. So whenever it is starting to diverge, we are converging and converging. So this was really cool what we achieved here. And if we compare this in the terms of the results, numerical results, so on the left-hand side, this TSIF is the implementation where you have no information to reset your bias. So this is just counting steps. And we did this first. In the first row, we have just the geometry, then geometry and the terrain, so from the first paper, and then geometry and our unsupervised learning approach. So those two are quite close to each other, but if we remove totally the geometry, now the unsupervised terrain representation is dealing better because we are getting more and more information about the terrain comparing just to pure classification, where the surfaces were totally homogeneous without fine details of the interaction with the terrain. And to say how hard was the process, for this terrain, we were like walking almost whole day. It was 715 meters, 4,054 seconds, but this is just the only test part, not the learning part. And it was 6,658 steps. We also covered the data with the geodesic scanner, so we have the proper map. We had the overlooking the OptiTrack system, which was giving us the right pose of the robot, so we can have this ground truth. So it was like a couple of days of setting up the experiment and then whole day of running it. So just the side note is that the sparse map for these trials was created based on the previous independent runs. So we had some runs for getting this sparse map, and then we are doing the testing. And just to get this small notion, this is like a side trip with this haptic transformer, but I wanted just to show the latest result that we get. So we thought about, so we had the transformer using sequences, also then in images. So then we thought it might work for signals as well. And it turned out that it's doing really well. If we look at the graph that we have here, on the right-hand side, we have the CNN, RNN. This is the implementation that we had in this classification at the part where we have the supervised learning in the localization. So it is doing really good in terms of accuracy, but this is very large model and you have a lot of CPU inference time. This is in milliseconds and logarithmic scale. But then if we use transformer, we are close to those results. This is these HAPT2, but we are having less than, so very little parameters comparing to CNN, RNN. And the inference time is way better because for that you have something like 11 milliseconds, and here we had something like 5 milliseconds for the same results. And our claim was that if you want to run it, for example, on the limited resources like NVIDIA Jetson or something like that, it is way better to have such small. So we are not fighting in terms of accuracy. We were showing that we can have it working really well on the real robotic system and in embedded device. So this was the point in here. So just to sum up, so I was showing the localization of the robot based on the terrain description. We are using Monte Carlo sequential particle estimator, and we did it for supervised and unsupervised learning approaches. And then at the end, I've showed also some words, so some slides on the haptic transformer for efficient terrain representation. At that point, I would like to thank my co-authors and colleagues from those papers. Is the Jakub Bednarek, Michał Bednarek, Mikołaj Łysakowski, Michał Nowicki, Dominik Belter, and our collaborators from ETH Zurich, University of Oxford, University of Edinburgh, PISA, and the startups that we have. So it was Anybotics, Cube Robotics, and then KGH Cuprum, and it was in the Think project. And I was just wanted to show where we use it. This is, I don't know how to start. It's going to start, yes. So in the Think project, we did some trials underground. So the first trials were in the salt mine, so it is 600 meters under the ground. So these are initial tests from the first years who were trying if the system is working. And then we moved on to, this is KGHM, this is copper enrichment plant. It was very, very dusty there. And now we are in the drying facility in the coal mine. So this is the point cloud with the temperature, showing the temperature, what is happening there. And this is 800 meters beneath the ground. The slope is 15 degrees, and we are building this thermal map so we can do the maintenance inspection of the infrastructure in the mine. So this is where we use it. So thank you very much, and I'm happy to answer the questions.
Great, thank you. All right, do you have questions? Yes.
Okay. So, hi, thanks for the text. So would it be feasible to like do the simultaneous localization and mapping using only like this like inputs from the sensor and like from the leg sensors? And because right now, I guess you
yeah, so we are just localizing now.
Yeah. So what would be the problems? And
okay,
I'm interested.
So it was one of the objectives of our project, and it turned out to be really hard. Surely it's gonna be very imprecise and very sparse. So we thought about like filling the gaps. So if you touch the ground, for example, you can assume that it's in some vicinity of this point. This is the same region of, for example, the type of terrain. But then you have to do either active probing, so you have to go and check, and then you're gonna be really slow, or you just walk and assume that you're gonna get back at the same path. But this is, you have very little information from that.
All right.
So how important was the choice of the filter? Did you try other filters like Kalman filter or other filters, or?
So this was the part done by our colleagues from Oxford. So they did the research for geometry. So they did the same stuff for the geometric cues, and then we transferred the system to the cues from terrain, for example. So this was what we did. So they already tried it, and it turned out that the Monte Carlo is the best choice for them.
Thank you.
All right. Do we have more questions? Okay.
So I was wondering whether there's a situation that the robot cannot use any vision, or whether you just wanted to have this clean case for now and later you still want to combine it with vision information.
So as I mentioned at the beginning, we had this scenario in the project. When you walk with the robot to some point in the mine, in the tunnel, so you gather the map, and then something happens. So the wall collapsed, or you lose your sensors, for example. So then you have to have a way to retreat. So this was our assumption. Let's say scenario.
Okay. Well, we still have a few minutes. Are there more questions? If not, let's. Oh, Maciej.
So what kind of terrain did you have like underground? Was it different than in this testing field that you had?
Yeah, so the main problem is that it is quite hard to gather data underground because they are just letting you for the 4 hours. So we did some terrain classification, but not the full-blown system as we showed it in the lab. So this was the point.
Okay.
All right. Okay, I don't see more questions, so let's thank once again our great speaker. Thank you.
Thank you.
All right, and yeah, it looks that we reached the end. So we would like to thank once again all the speakers for very interesting talks. Also for coming here to Warsaw from Kraków, from Poznań. We'd like to thank our host, Allegro, for helping us organizing this event, and our sponsor as well. And we invite you to stay with us for the after party and networking part. Enjoy, have fun, and yeah, all the best. Thank you.